interaction of energy with the target. Radiation that is not absorbed or scattered in the atmosphere can reach and interact with the Earth's surface. There are three forms of interaction that can take place when energy strike or is incident upon the Earth's surface. They are absorption, transmission, and reflection. Some amount of incident energy, if we consider this one as the incident energy, some amount of incident energy will be absorbed by the Earth surface material. Some amount of energy will be transmitted through the Earth surface material, and some amount of energy will be reflected back. The radiant energy must be conserved. That is, it is either returned by reflection or transmitted through a material or absorbed and transformed into some other form of energy. The net effect of absorption of radiation by most of the substances is that the energy is converted into heat, causing a subsequent rise in the substance's temperature. Hemispherical absorptance is the ratio of energy that is absorbed by the surface in a specific wavelength and the radiant flux incident to the terrain. For example, if this is the absorbed energy and this is the incident energy in a specific wavelength on the terrain, then this is the absorptance. So it is basically the ratio of these two substances. Hemispherical transmittance is the ratio of energy that is transmitted through the surface in a specific wavelength and the radiant flux incident to the terrain. Similarly, hemispherical reflectance is the ratio of energy that is reflected by the surface in a specific wavelength and radiant flux incident to the terrain. These radiometric quantities are useful for producing general statements about the spectral reflectance, absorption and transmittance characteristics of terrain features. In fact, if we take the simple hemispherical reflectance equation and multiply it by 100, we obtain an expression of percent reflectance as shown over here. This is often used in remote sensing research to describe the spectral reflectance characteristics of various phenomena. The amount and properties of reflection will depend on the wavelength of the energy and the material and condition of the surface. Surface of the material plays a vital role in this case, and it needs to be discussed elaborately. So there are actually two general types of reflecting surfaces which interact with the electromagnetic radiation or electromagnetic energy. One is the specular reflector and another is the diffuse reflector. In this figure, we have shown ideal specular reflector, where the angle of incidence and angle of exitance or angle of reflection are same, and the entire incoming energy will be reflected back in the opposite direction. Then we have the near perfect specular reflector. Actually, on the Earth's surface, we don't find any real specular reflector. Specular reflectors, whatever we find on the Earth's surface, are actually near perfect specular reflector. In case of near perfect specular reflector, most of the energies, most of the incoming energies will be directed back in the same angle, but in the opposite direction. But some amounts of energy will also be reflected in other directions. The amount of energy will be very minimum, definitely. Specular reflection occurs when the surface from which the radiation is reflected is essentially smooth, like mirror like surfaces. Several features we have for the several features we have a flat surface, for example water bodies, etc., and we get specular reflector. If the surface has a large surface height variation compared to the size of the wavelength of the incident energy, the reflected rays go in many directions, depending on the orientation of the reflecting surfaces. This diffuse reflection, this is called diffuse reflection. And here I have shown one ideal diffuse reflector in which the entire incoming energy is being directed in all possible directions and also in equal amount or same amount. But definitely there is no ideal diffuse reflector on the Earth's surface. Rather, we have near perfect diffuse reflector, where most of the energies will be directed in all possible directions in equal amounts, but some amount of energy will be directed in the opposite direction of the incidence angle, and this is ideal specular reflector type or specular reflector type characteristics. Now, rough surfaces act like diffuse reflectors. If any diffuse reflector reflects in such a manner so that radiant flux leaving the surface in constant for any angle of reflectance, then this reflector is called the ideal diffuse reflector, or this ideal diffuse reflector is also known as Lambertian surface. We have used the term hemispherical to measure the reflectance, absorptance, and transmittance. Hemispherical measurements account for all energy contained within a hemisphere above a surface or object of interest. For example, diffuse reflection is hemispherical, where the specular reflection is directional. Directional measurements actually account for the measurement in a particular direction of illuminating or viewing. In remote sensing, we are generally interested in measuring the hemispherical or diffuse reflectance properties of terrain features, because in directional or in specular reflectance, the energy is reflected in a single direction and the sensor must be placed in that specific direction, otherwise the object will appear as black, because there will be no light to record by the sensor. Now, spectral reflectance curve is another important issue that requires to be discussed in remote sensing. Spectral reflectance curve shows the relationship of electromagnetic spectrum with the associated percent reflectance for any given material. And as you can see in this figure, the x-axis is representing different wavelengths and the y-axis is representing the percent reflectance. And as you can see, for different types of earth surface materials, the reflectance is different for different wavelengths. And if we consider a specific wavelength, for example 1.2, then the reflectance is different for different types of earth surface materials. And if we consider a specific earth surface material, for example vegetation, it has different amounts of percent reflectances for different wavelengths. For any given material, the amount of solar radiation that is reflected, absorbed or transmitted, it varies with the wavelength, as we have discussed earlier. In this example, as you can understand, that when we use more and more wavelengths, the plots tend to show more separation among the materials, and that is basically the backbone of the hyperspectral remote sensing. The improved ability to distinguish materials due to extra wavelengths is the basis of multispectral and hyperspectral remote sensing. Now, for example, if I am collecting only one band in the blue region, that is 0.4 to 0.5 micrometer, then I will have only one value for the blue band, then only one value for the green band, only one value for the red band, and only one value for the near infrared band. Now, the curve will look like this. The curve will look like this. Now, if we want to get a curve like this, I mean this one drawn in this figure, then we have to collect imageries in all possible wavelengths, and then only we can get this type of curve. And this is only possible in case of hyperspectral remote sensing. Multispectral remote sensing cannot give us this type of curves. Let us consider examples of targets at Earth's surface and how energy at the visible and infrared wavelengths interact with them. Two very important materials on the Earth's surface are vegetation and water. So, let us try to understand the reflectance characteristics of vegetation and water. First, the vegetation. A chemical compound in leaves called chlorophyll strongly absorbs radiation in the red and blue wavelengths, but reflects a higher amount of energy in the green band. Leaves appear greenish to us in the summer when chlorophyll content is at its maximum. In autumn, there is less chlorophyll in the leaves, so there is less absorption and proportionately more reflection in the red wavelengths, making the leaves appear reddish or yellowish. The internal structure of healthy leaves act as excellent diffuse reflector or diffuse reflector, particularly in the region of the near infrared wavelengths. If our eyes were sensitive to the near infrared wavelengths, trees would appear extremely bright to us, as the vegetation reflects a very high amount of energy in the infrared region. In fact, measuring and monitoring the near infrared reflectance is one way that scientists can determine how healthy or unhealthy the vegetation may be. Healthy vegetation reflects more near infrared light than unhealthy vegetation. Now, in case of water, Longer wavelengths, longer wavelengths means visible and near infrared radiation is absorbed more by the water body than the shorter visible wavelengths. If we compare the visible light, and visible light means the blue, green, red, and the near infrared radiation, then definitely the near infrared radiation is more absorbed by the water bodies. Basically, with the increase in wavelength, the absorption property of the water will be increased. Thus, water typically looks blue or blue-green due to stronger reflectance at the shorter wavelengths, and it appears darker if viewed at red or even NIR wavelengths. If there is suspended sediment present in the upper layer of the water body, then this will allow better reflectivity and a brighter appearance of the water. The apparent color of water will show a slight shift to the longer wavelengths. Suspended sediment can be easily confused with shallow but clear lake water. Since these two phenomena appear very similar, chlorophyll in the algae absorb more in the blue wavelength and reflects the green, making the water appear greener in color when algae are present. The topography of water surface, whether it is rough, smooth, floating material, etc., can also lead to complications for water reflected interpretation due to potential problems of specular reflection and other influences on color and brightness. We can see from these examples that depending on the complex makeup of the target that is being looked at and the wavelengths of radiation involved, we can observe different responses of the mechanisms of absorption, transmission, and reflection. By measuring the energy that is reflected or emitted by targets on the Earth's surface over a variety of different wavelengths, we can build a spectral response of that object. By comparing these response patterns of different features in different wavelengths, we may be able to distinguish between them where we might not be able to if we compare them at one wavelength only. For example, water and vegetation may reflect somewhat similarly in the red band, but almost always separable in the near infrared band, because in the near infrared band vegetation has very high reflectance. It appears very bright, but water appears very dark because of the high absorption. Spectral response can be quite variable even for the same target type, and can also vary with the time and also based on the location. For example, the greenness of a vegetation species may differ in different seasons. It may also differ in different location because of health and condition may vary with the change of soil type and weather. So, knowing where to look spectrally and understanding the factors that influence the spectral response of the features of interest are critical to correctly interpret the remote sensing imageries. The nature of interaction of electromagnetic energy with the object can lead to identify different types of Earth surface materials. The basic property by which an object can be identified is called signature. As we know, a person can be identified by his or her signature. All the properties of an object help us to identify it. For example, golden color of a wheat field indicates that the crop is matured. In remote sensing, spatial, spectral, and temporal variations are the major characteristics of identifying an object. Spatial means space related information, spectral means reflectances in different spectral bands, and temporal variations means differences in reflectances because of the change in time. Spatial signatures are the arrangements of terrain features like shape, size, texture, etc. Spectral signature indicates the change in reflectance of objects with different wavelengths. Temporal signature is the change in reflectance with time. Therefore, by proper investigation of these three signatures, we can get a clear understanding about the object type and its surrounding. Now, this was all about the interaction of energy at the terrain. Now, after the interaction at the terrain, some amount of energy will be reflected back. The radiant flux reflected or emitted from the Earth's surface once again enters the atmosphere, where it interacts with various gases, water vapor, and atmospheric particulates. Thus, atmospheric scattering, absorption, reflection, and refraction influence the radiant flux. Once again, the energy will be modified by these atmospheric interactions. However, we are not discussing these atmospheric interactions again, because already we have discussed all these interactions in the previous section.